Welcome back, CIS 1400. It's good to see you all again. So let's get into this first module and we'll talk about hardware, networking, and just generally how computers and programs work in general. So let's get into this presentation. So first, you're going to want to make sure that you do the reading. The reading is Chapter 1. You want to be introduced to computers and programming. In the reading, they discuss hardware, computers, how they store data, how a program works, different types of software. The presentation that I'm about to give you is not meant to be a replacement for the reading. Please make sure you do the reading, as when we get to the quiz at the end of this module, I will be pulling questions directly from the reading that you will be responsible for that we may not cover in this presentation. This is just meant to be a supplemental activity to the reading that you have to do. So please, if you haven't done that yet, go back and read the required chapter. So, hardware and software. Hardware generally refers to all the physical components of the computer. If you were to break open the case or open up a laptop, you would see all the pieces of hardware, but you can also see hardware out on your desktop as well. Inside the computer, you'll see things like the CPU, also known as the central processing unit. That would be better known as the brains of the computer. That's what does all the processing for every application that you do. It takes in binary signals, electrical current on and off, and runs them through very basic logic gates, and the order in which those logic gates turn on or off or create more refined circuits gives us everything that we do with a computer. It's pretty interesting and actually quite simple to think about. Another piece of hardware might be your main memory, or what we'll call random access memory, or RAM. That would be the short-term storage device for the PC that would hold all of the pieces of information that the CPU needs to in order to perform its processes. So any kind of information or variables that you might store in a program, or if you're loading a piece of software, all of those instructions are going to get stored into RAM, and then the CPU will request information from RAM and process it, and then return information back to it. As soon as the computer goes off, anything that was stored in RAM or in main memory is lost, so we would say it's volatile storage. But it is actually very short-term storage, so it's meant to get processed by the CPU at some point in time. If you ever find that your computer's acting sluggish or slower than normal, maybe it's because you have so many processes going on and it's just having a hard time finding a place to store all the information it needs to store in order for the CPU to process it. So a simple thing that you can do to increase the performance of your computer is to actually add more random access memory to the PC, usually double it or whatever it may be. Your computer might currently have 4, maybe 8 gigs of RAM. If you could increase that from 4 to 8 or from 8 to 16, you should see a pretty remarkable increase in performance. Replacing the CPU is not something normally done, but increasing RAM is a very easy fix and actually a very economical fix for a computer, especially one that might be performing slowly. Another piece of hardware you should be well aware of are secondary storage devices. Those would be those pieces of hardware like your hard drive or maybe a flash drive. Those would be more long-term storage. Stuff would get stored on there to be used across multiple days or multiple periods of time. So that's a pretty integral piece. Then you've got different input-output devices, or I/O devices. Input devices being the keyboard or the mouse or maybe even the webcam. Output devices being the monitor or a set of speakers. But those are all the different pieces of hardware that might go into it. There are many others like the motherboard, ROM, read-only memory, other pieces of circuitry that might be in the PC. But for the main parts that you need to be aware of, you've got the CPU, RAM, different storage devices, and different I/O devices, at least for this course. Software is the part of the computer that stores all the instructions on how the hardware is supposed to perform its task. So basically software breaks down into two specific parts. You've got system software and application software. Your system software is your operating system. For me, right now I'm currently running Mac OS. You might be running Windows or Linux. On your mobile devices, if you have an iPhone, you'll be running iOS. If you have any other type of phone, you're generally running Android as being the most popular operating system for a mobile device. Your your system software basically is the communication between you and the hardware. It tells the CPU what circuits to use. It will allow it to run programs instead of, they don't run simultaneously, but turn them on and off and run them one at a time, but so fast that you'll never understand that only one thing is running at a time. Application software is that software that you're probably more used to seeing actually run and experience, things like Microsoft Word or PowerPoint or Excel or Google Chrome or Internet Explorer. Those are pieces of application software. Those are actual apps that you're using on your computer or on your mobile device that you are communicating with and working with specifically for a given task. So those are the two different kinds of software. We are going to be writing in this class application software. Nothing as detailed as usually what you would see yourself using on a day-to-day basis, but small pieces of script that will do a desired task, which is still a piece of application software. Okay. Now we start talking about software and we start talking about hardware and how they all work. Hardware is a really basic kind of unit here that can't really do a whole lot. So since the hardware in the computer, specifically the CPU, really can only measure electrical impulses on and off, we generally represent them for our understanding in a base 2 number system or something called binary, which you can see down here. The only images associated with binary are zeros and ones, whereas where we're used to a decimal number system, oops, sorry about that, in which the images are 0 through 9. So we have 10 images to help us support our number system, where a computer, even though it doesn't even have images, we use the images 0 and 1 to help represent what the computer is doing. These are all different types of number systems that are used either by us or by a computer system, or even by a different culture or group of people. So a number system is simply just a set of predefined symbols that represent given quantities. When I have the number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, those are all just simple images that represent a quantity. As soon as I start running out of images to use, we use different placeholders to represent various multipliers of those quantities. So in our number system, we represent the number, say, 17 as a 1, 7. But realistically, the 1 being where it is in the number 17 represents 10 units, and the 7 represents only 7 single units, so 10 plus 7 gives us a full 17. 105 means I have 100 units and 5 single units, so that gives me 105 altogether. Binary, octal, hexadecimal, they all do basically the same thing, it's just the base changes, so the way in which I do the multiplication changes a little slightly. So computers use a base 2 number system, a binary system, a binary digit, which we'll commonly refer to as a bit. That's what a bit stands for, a binary digit, B for binary, IT for the last 2 units of digit. We'll represent those with 1s and 0s, okay? And then as you stack certain bits together, you get certain quantities of memory. You put 8 bits together, you get a byte of memory. Okay? Stacking bytes together will get you more commonly known memory amounts, such as 1,000 bytes being a kilobyte, and 1,000 kilobytes being a megabyte, and so on and so forth till you get your gigabytes and terabytes and petabytes and so on and so forth. The number system for a computer system is really simple to work with. It's just a matter of understanding how those binary digits relates back to our decimal digits in any way. And so here you can kind of see how those binary digits kind of roll over. I don't know why it's asking me to sign into this, but we will. Okay, let's see. Oh, here we go. And if I run this little widget here, you can start to see how the binary digits as they increase. We really are only working with the digits 1 and 0. And if I reach something that exceeds that digit, that highest digit 1, it has to roll over to the next column, just like our number system does here. As it reaches 9, you see it roll over to a 2 here in the tens placeholder. And then it will reach the 9 again, and it will roll over to make a 3, which means now I have 10 more of those same units that are coming from the previous placeholder, and so on and so forth. But in a binary system, or octal system, or hex, they just all roll over at different images at different times. Binary rolls over every 2 digits. Octal, you should notice it rolls over every 8 digits, runs through the digits 0 through 8, or 0 through 7. Hexadecimal has 16 images, so you'll see it go through 0 through 9, and then work its way into an A, a B, a C, a D to represent the 10, the 11, the 12, and so on and so forth, all the way up to 15, and then finally rolls over. So the number system, whatever it is, it doesn't make a whole lot of difference in how you work with it. We just need to know that we're used to a binary or a decimal system, and computers work on a binary number system because it just needs 2 values. Its signal is on or it's off, and that's all it can be. Okay. So a computer, since it stores everything as a symbol of on and off signals, we still have to represent it with 1s and 0s, and then we take those 1s and 0s and convert them back into something we're more used to so that we can visualize it ourselves. So a bit can be used in a very limited way to represent numbers. It just depends on whether the bit is on or off, and where you put it changes what the value is with that bit. So for instance, I have here a byte of memory that is considered 1001101. Now looking at this, the same way we do with a base 10 system, this is technically a 2 to the 0 power, or technically just a single unit 1. And this bit here would be considered 2 to the 1st, and the next one 2 to the 2nd, 2 to the 3rd, to the 4th, to the 5th, to the 6th, to the 7th. Gives me a full byte of memory. And as I go through and add these up, 2 to the 7th being a full 128 units, a 2 to the 3rd, 2 to the 4th being 16 units, 2 to the 3rd being 8 units, 2 squared being 4 units, and 2 to the 0 being 1. If I take the 128 plus the 16, the 8, the 4, and the 1, I get 157 in our decimal number system. So the fact of the matter is I can represent any value I want in decimal in binary, and I can take any binary number I want and represent it in decimal, which is really nice because that's how everything in a computer system works. Everything gets drove down to some sort of number. We'll generally write the number out in base 10, but the computer will convert it and work with it in base 2. For instance, the character A, based on an ASCII table, you'll represent the A in uppercase A with the number 65. Well, a computer then translates that number to binary, which was a 1000001. So 64 plus a 1 makes 65. It represents that number as that binary digit, which gives me that character. And then the CPU can ask for instructions from RAM on how to represent that on the screen, or whatever it may be, based upon its encoding in binary and what it's relating to, so its context. I have binary digits and decimal digits for every character on the keyboard. A, B, C, D, everything we want. Colors are the same way. You have red, green, blue values, RGB values. Those values range from 0 to 255. And as I start putting those triplets together, those 3 bytes of memory, I get a pixel. And your screen is built up of thousands, if not millions, of pixels. So every single one of them can be represented with a 3-byte number, a 3-byte integer. So it's actually pretty interesting how everything breaks down to a number in some way or other, whether that be a character or an actual digit, or maybe a pixel on the screen, an RGB value, a sound that's coming through your speaker, which has a pitch and a frequency. All of those things relate back to numbers, and so if we can relate it to numbers, we can relate it in binary. If we can relate it in binary, then we know it's an electrical signal that the CPU can process, which means it's something the computer can work with. So the nice thing about computers, everything's a number, and we can manipulate those numbers as much as we want. Now, how a program actually works when you're actually doing it, we do not code in binary. That would just take way too long and be way too tedious. We haven't done that in many, many decades. So what we do is we leverage the CPU and its logic gates to perform the calculations for us, but the CPU still can only deal in binary. So what we need to do is write code in what we call a high-level language, okay, which is going to become our source code. That high-level language could be anything like Python code, or Java code, or C++, or JavaScript. Whatever it may be, it's something that's more English-like in manner, okay? And then based upon the language, it will go through one of two processes. If it's, say, Java, okay, or C, it's going to go through what we call a compiler. And a compiler is a special program that's behind the scenes in your computer that will take your source code and turn it into something the machine understands, what we call machine code. And that's what the CPU can then process and then deliver whatever output that we're going to get on the screen. Now let's say you're coding in Python. Python is the source code, but then it leverages something called an interpreter. An interpreter acts a lot like a compiler. It will still translate everything from what you write into the ones and zeros of the machine, but it will do it one line at a time instead, whereas a compiler will translate the entire file into machine code before output is generated, whereas an interpreter will do it one little bit at a time and give you output as it goes. Generally, you'll find interpreters are faster than compilers, but the issue is if you do things one line at a time, you may run into errors in, say, line 25 of your program, and you won't know it until you get there and you've already gotten some output and your program just suddenly crashes. Whereas with a compiler, generally what you'll see is if you're running your program, it will find the error before it even allows you to run the program, so you have a time to go back and work with it. Most languages will leverage a compiler. Some will leverage an interpreter. There are also those that do both. Java actually does both, a compiler and an interpreter to work with it. Why it does that? It makes it a little bit easier to make it platform independent so that you can code and execute from one platform to another, meaning Windows, Mac, and Linux, or whatever it may be. But they all have their advantages and disadvantages, so you just kind of have to pick the tool that is right for you as you're going through certain things. Now, as you're coding, one thing we should be aware of is that you are going to be coding in something called an integrated development environment, an IDE. There are many different IDEs out there. I introduced my favorite Python IDE in the introduction video, PyCharm. But if you're used to any others, you're more than welcome to use those throughout the course. Visual Studio is a great editor, and I know it's on the labs in the at College of DuPage. PyCharm should also be on the labs at College of DuPage. That was kind of a recent addition last year. But you can also use Eclipse with Python plugins, maybe even NetBeans or Atom. But depending on the language, depending on what IDE you choose to use and what you like to do, you can still code everything that we're going to code and work with everything we're going to work with. It all just really comes down to personal preference and what you want to do. Listed on the screen here is an IDE called Eclipse, and they're running C++ code in it. I generally use Eclipse for Java code, but PyCharm is awesome here for Python scripts, and there are also different IDEs out there. So feel free to click on any of the links here, and they will bring you to a place where you can download each one of them. Please click on the PyCharm one. It'll help you download PyCharm, and we'll get into how to work with all of that more in the next module as we start coding certain things. Okay. Now, like I said, this was meant to be a supplemental video, not the end-all be-all. So please make sure that you have done that reading and you are ready for the quiz that you are going to make sure that you have completed by September 16th. But in the meantime, over the next week or so, there is an assignment that you will find on Blackboard in Module 1. It is two worksheets that have a series of videos in each one. I can show you those really quick and what you're going to be doing with them. So let me come out of here. And in that, let's see if we can find those. Module 1. Oops, they're not here. Where are they? So here's an example of the networking video worksheet that you have linked in the assignment. You are going to answer each one of these questions. You can just type your answer right in here. Who invented the internet? We can say it was Big Bird. And hopefully you know it's not Big Bird. Who invented the internet? And Al Gore, which again is untrue. But the inventors of the internet will be portrayed in the video. All you have to do is simply click on the link if you wish, or whatever it may be, or highlight that link and copy and paste, but it will bring you to this particular video here, what is the internet, and you just need to watch it and fill out the paperwork as you go. The questions should go in line with the video, so you should be able to fill them out as you're going through it. Please read the questions before watching the video. You'll know what to find, and go back and rewatch the video if you miss any. There is the networking video, and there is a hardware video that you have to go through. Please go through both of them. I would suggest the hardware video first and then get into the network video. Outside of that, I hope you enjoyed Module 1. I know it's a pretty basic and simple module to start things off. Second module, we will begin getting into logic and design and some simple programming statements in Python, so we'll actually do some coding, and so that video will probably be a little bit longer or maybe broken into a series of videos. So be prepared for that, and make sure you hit these due dates. So if you have any questions, I will open up a discussion thread in Module 1 so that you can ask them, and then I will answer, and then hopefully if anyone has the same question, they'll see it in the discussion thread and not have to ask it several times. But if you have anything that you need to bring to my attention personally, please feel free to email me anytime. Okay, that about wraps it up for Module 1. Let me know what you think, and I look forward to seeing you again in Module 2.